Okay, kids, let's do some more series. Here's our friend Colin Maclaurin, right? So I want you to write out the first four terms of a Maclaurin power series. Notice I don't tell you the center, right? Because what's true about Maclaurin? Always centered at zero. Every time you have Maclaurin, they don't have to tell you the center. The expectation is you know the center is zero. So let's build this from scratch. And again, by the end of the today, our goal is to try to avoid building by scratch. Which means we want to try to find some patterns. Whoops, sorry. So here we go. The power series, so e to the x is exactly equal to a polynomial series that is built. And I want 1, 2, 3, 4 terms. Since the center is 0, this is going to be x to the first, x to the 0, x to the first, x squared, x cubed, meaning it is a third order because I've stopped with the third derivative. Now, how do I get those values? Right, we need f at the center, and we need f prime at the center, and we need f double prime at the center, and we need f triple prime at the center. Love e, because e is its own derivative, so f of 0 is e to the 0, which is 1. F prime of e to the x is e to the x, right? So I just get a bunch of 1s here, don't I? So I'm going to put 1 on all of these lines, but don't forget the factorials. And then remember, this goes on forever and ever and ever. So what does e to the x look like? E to the x can be represented, this exponential function of the natural number can naturally be represented with an infinite polynomial that is 1x to the 0 plus x to the first plus x squared over 2 factorial plus x cubed over 3 factorial and forever and ever and ever. Whoops. Which means I can write the nth term for this, right? Isn't this x to the n over n factorial? OMG, e to the x, right? Pretty famous, pretty easy power series, right? It's just x to the, whoops, I forgot 1. That's a 1. It's just x to the power over that factorial. No changing of signs, all positive. And remember, there's really a 1 factorial under here and a 0 factorial under there. OMG. Crazy. Done and done. What if I wanted you to do so this is for e to the x centered at 0. What about e to the x centered at 1? Now, unlike the previous, I'm telling you I want you to shift e to the x. I want you to shift e to the x. I have a new center. The minute they say Taylor, they have to give you a center. They have to. Even if that center is 0, if they use the word Taylor, must be followed with a center. So e to the x centered at 1, where I want you to shift it, one, two, three, 1, 2, 3, 4. Oh man, I didn't leave myself enough space. I want you to take e to the x and shift it over to x equals 1. Which means you do have the factorials of 0 factorial, 1 factorial, 2 factorial, and 3 factorial. But you have here to the first power, to the second power, 0, 1, 2, and 3. And then, of course, dot, dot, dot. You don't have just x anymore. Shift it. Shift it. Oh, I should have left that blue. 1 to the right. That's where my center goes. And then when you evaluate right here, you plug in what to the derivatives? 1. So 2 places the center has to go: into the function, into the derivatives. E to the x shifted over is f of 1. What's f of 1? E. X minus 1 to the 0, which is just 1 divided by 1, plus f prime at 1. E times x minus 1, plus f double prime at 1. E times x minus 1 squared over 2, plus f double prime at 1. E over 6, or 3 factorial, don't care what you write, x minus 1 cubed. Okay, what if I wanted you to use this approximation? Use the first 4 terms to approximate e to the, not e to the 1, right? E to a number close to 1, so maybe 1.1. So use the first 4 terms, which means truncate the polynomial. So e to the 1.1 is approximately e plus e times 0.1 plus e divided by 2 times 1.1 minus 1 squared, yada, yada, yada. Do that calculation just for the heck of it. And then on your calculator, do e to the 1.1 and see how close it is. It's going to be freaking close, right? That's what your calculator has in its memory bank, right? It's not trying to approximate, right? It's just plugging numbers into a polynomial, and it can do it really quickly, right? Crazy. All right, so I want to avoid building. Remember, that was my goal. So I want to know how to take e to the x and just shift it myself, right? Shift it to a new center, right? So if I know this formula, e to the x is a pretty easy polynomial. I don't think I have to build it by scratch each time, right? It's just, right, x to the 0, x to the 1, x to the 2, x to the 3, x to the whatever, divided by the same factorials. And if I need to shift it, I just need to evaluate this at the center, right? That's the only thing I have to change, is that coefficient in front, right? I still have, instead of 1, I have an e. Instead of this 1, I have an e. And then instead of x, it's x minus 1, right? Instead of each one of these 1s, I have an e. I have f of 1. Kind of cool. So again, once you have a power series that we know, for instance, geometric, or now we have some pretty famous ones. In the last video, we built the series for sine and for cosine, and now I've done e. Those are some, and then of course, along with our geometric that we did before, any geometric series. If you remember how to build any geometric power series, and then you remember what sine, cosine, and e look like without having to build it from scratch, we are going to build new power series that are combinations of these without building and using Maclaurin or Taylor. So for example, here is a geometric series, right? I recognize the pattern, 1 over 1 minus negative x. So this is my function. What if I want a power series representation for it? Knowing my geometric series, it's a r to the 0, a r to the 1, a r to the 2, a r to the 3, done and done. Geometric. What if I give you this function though? Called g of x. Notice that it's the same function except I multiplied it, right? G of x really is x times f of x. So multiply f of x by x and multiply f of x times x. That's just distribution, right? So multiply term by term. Multiply x on the left, multiply x on the right. Beautiful. Now, of course, I could have done this anyway without that, right? I could have just said a was x and I would have done the same thing. But this idea of manipulating a known power series, right, to create a new one, pretty powerful, especially when you're dealing with not geometric. So what if I ask you for the 4, notice I ask you for non-zero this time. Non-zero, first 4 non-zero terms and the nth term. Don't give them the nth term unless they ask for it, of this function, and I'm telling you it's Maclaurin. So cosine, we built that yesterday, right, in the previous video, and I said cosine was even, so you need all the even powers, keep all the even powers, knowing that all the odd powers are zeros. So they wanted the first 4 non-zero and the nth term. So this is x to the 0. So 0, 2, 4, and 6 with the appropriate factorials. Here's my nth term, right? I have x to even powers divided by those same powers factorialized. And then this is my alternator. Right? So that I built from scratch, but now I know it. Hopefully you want this to be one of your known. You want cosine x to be a power series you just know. You don't have to build it. Even powers alternate the signs. But what if I asked you for cosine of 2x? If you wanted to build this from scratch, you would have to find all the derivatives of cosine of 2x, plug in, blah, blah, blah. It wouldn't be terrible, but instead of doing that, take the known, notice that cosine of 2x is just a composition. Do you see that? So take f of x, here's your polynomial when I just have x, and change the x, which means change the x to what? 2x, right? Change the x to the 2x. Bam! Boom, 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 boom. Everything else stayed the same. Composition. I showed you on the previous slide how I took one function and multiplied by x. This time I composed 2x, but instead of doing all the derivative work and everything, bam, I'm done. What if I asked you to multiply this one by x? What would you do? What if I wanted x times cosine of x? That's not a composition. That is just a multiplication. Take your known and multiply it by x on the left and multiply it by x on the right. Which is just distribution. Right? So 1 times x is x. X squared times x. X to the 4th times x. X to the 6th times x. Notice what I did here. X to the, right? Every time, what happened to my old one is I added an right, a power here to the exponent. So that's where this came from. So notice that cosine is even. So cosine has odd powers. I'm sorry, has even powers. But when I manipulate cosine, I might hide, right? Do you see what happened there? If I manipulated cosine, I manipulated what it looked like. It didn't automatically have my even powers anymore. What about this? Given this geometric series with its infinite polynomial, find the infinite polynomial representation for this one. So you might be tempted to say, oh, snap, what I know and what I'm trying to find only differs by being squared. So why don't I just square both sides? Stop it. This is true, right? Because it's 1 squared and 1 minus x squared. That's what I have. Right? Hello, squaring polynomials, right? You can't distribute that, right? 1 plus x squared, even if I just do the first 2 terms, is not just equal to 1 squared plus x squared, right? That doesn't work. So bother. I would like to do a manipulation. Now I could build this one. It wouldn't be terrible. I could find the derivatives and all that. But what if I don't want to? Remember, that's my goal. I don't want to build from scratch. So check out what I did. I took the derivative of the left side. Right? Do it right. I can't square both sides because this is an infinite polynomial, but I can take the derivative of both sides, because taking the derivative of a sum is just taking each separate derivative, right? So if I take the derivative of the left, you see what happens? Oh my gosh. The derivative of my given is equal to what I'm trying to find. So if I take the derivative of the left side and get what I'm trying to find, and I want its infinite polynomial representation, just take the derivative term by term. So the derivative of 1 over 1 minus x is equal to the derivative of its infinite polynomial representation. The derivative of 1 minus x is what I'm trying to find. So to find its infinite polynomial, just differentiate term by term. And polynomial derivatives are sweet. The derivative of 1 is 0. The derivative of x is 1. X squared is 2x, x cubed, and blah, blah, blah. And I gave them 4 terms, assuming that they asked. Okay, pretty cool. So you can avoid the building or the construction process by manipulating series I already know. And the series you know are geometric, sine, cosine, and e. The things that you can do are composition, multiplication, and differentiate both sides. You can't square. Check this one out. What if I want a power series representation for ln of 1 plus x? Right? What if I want a power? So to do a power series, I would have to do that derivative, right? And then the second derivative, and then the third derivative, and then use my, right? Use my plugging in factorial, and dividing by factorials and all that. But check this out. isn't it true that the integral of 1 plus x is ln of 1 plus x, right? Think about that for a second, right? This is u to the first, right? And the antiderivative of u to the negative 1, right, or 1 over u, is ln of the stuff, as long as the derivative of the stuff is there and the derivative of the stuff is just 1. So if I want a power series for ln of 1 plus x, but, right, the integral of this other known, in this case, geometric series. So I know what the power series for the integrand is. Right? This is a geometric series. The geometric series representation, right? R is equal to negative x. So I did a r to the first, 0, a r to the second, a r to the 0, a r to the 1, a r to the 2, blah, 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 blah. I wrote out those terms. And then, but that is not what I'm after. That's geometric. So it was very easy to write out the power series. That's not what I want, though. I want the power series representation for ln of x, but the integral of 1 over 1 plus x is equal to the integral of its power series representation, but the integral of 1 over 1 plus x is ln of 1 plus x. And integrating 1 gets me x to the first over 1, x squared over 2, x cubed over 3, x to the fourth over 4, maintain my alternating signs. Wrote the nth term. I really should do this. Keep forgetting to do that. Just say that it keeps going. Crazy, right? Crazy. So that was, if you take these four, any geometric series, then sine, which is those, right, infinite polynomial with only the odd powers and alternating, SIGNs, cosine, which is, right, all of those, all the even powers with the factorials underneath, of course, alternating the SIGNs, e to the x, which has everybody positive and no one goes away and it has all the powers, 0, 1, 2, 3, 4, 5, divided by the factorials. You can change the center, right? Enter, right? Just, you can, if you're asked for a different center, right? Just evaluate the function and the derivatives at the different centers. You can make new Maclaurin series, either by composition, multiplication, adding and subtracting too, right? I could do that, right? That's not as interesting, but what if I said, I want the polynomial series for sine of x minus 1. Sine of x minus 1, I want the polynomial series representation for that. Well, write out the polynomial power series representation for sine of x, which is what? X minus odd powers over odd factorial. Alternate the signs. Minus 1. That's probably a little bit more interesting if I do cosine of x. Minus 1, because what does cosine look like? Oh, I should write that over here. Cosine of x, its power series representation is 1 minus the even powers over the even factorials. Minus 1. By combine like terms. There it is. Right? So you can do lot. The only thing you can't do, right? And now you know you can differentiate, and you can also take p of x and you can integrate both sides. Right? So the only thing you can't do is that squaring. No, can't square an infinite polynomial. Oh, and don't forget the interval of convergence, right? The interval of convergence, you can only, at this point in your BC calculus pathway, you can only talk about the interval of convergence if you have a geometric series. Because this is geometric, right? Remember, it was geometric and then it was a manipulation of a geometric, but if I manipulate it, I've got the same IOC. And, right, so I had my R was negative X. And that's why I got that. Okay. We are going to do a lot more with the interval of convergence, and we'll talk more about it in our live session with these known, right? Because for the interval of convergence for geo, you're all good. But you don't know about the interval of convergence for the power series for sine x, cosine x, and e to the x yet. Or any other series that you might build, right? But we will talk about that in our next live session. Now, before you go though, I just want to, these Maclaurin series are famous enough that they are in your book. You should remember a few of these. I will tell you the most famous. The first two, I don't really memorize because they're just geometric, right? As long as I know that here R is X and here R is negative X. I just know my AR to the 0, right? AR to the 0, AR to the 1, AR to the 2, blah, 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 blah. Those are two geometric. But notice the next three in line. E to the X, sine X, and cosine X. AP loves these. When AP tests you on manipulation, it's going to be one of these three. Right? They may do more, but they're definitely going to do one of those three. So know these series without having to build it, and then expect to manipulate it. And expect to manipulate it with composition or multiplication or differentiation or integration. Because composition, no problem. Multiplication, no problem. Differentiation and integration of polynomials are easy peasy. These are okay. I rarely see this one. I would just build this one myself. I mean, it's kind of nice, right? It's tangent. It's still odd. Just notice it doesn't have the factorials, right? And that just happens with when you build it, things end up canceling out, right? So odd signs still alternate, but just no factorials. This one I just did. This is really a manipulation of the geometric series here, right? I just did that one. So I don't really memorize this either per se, but definitely I do these three and I know my geometric really well. All right. So this is page 491 in your book, or just take a freaking screenshot of it. You should know those series really well. All right. Notice they are Maclaurin too. They're Maclaurin series, so they're all centered at 0. All right. Oh, firstly, these are all centered at 0. This is the interval of convergence. You shouldn't be surprised at the interval of convergence for these two because they are geometric. You should be surprised, but pleasantly surprised, at E, sine, and cosine. Their interval of convergence is infinite. They're awesome, right? They're awesome. Now, I'm just giving you that as a gift right now. We will talk about why that happens later. But for right now, you know that you only have to worry about the interval of convergence as geometric, which you always have known. The absolute value of R has to be strictly less than 1. And then remember, this one also came from geometric. So it is always also between -1 and 1. And you might know this thing might bother you. The fact that, wait, why is that equal to? Again, that is a question that I'm going to answer later, along with how do I know these interval of convergences are infinite, right? But that's a couple lessons down the road, all right? Now I will see you in our next live session.